next up, we're going to have our third speaker of the day, which is me, your host. So last summer, I did some really fascinating research at the Lawrence Berkeley National Lab here in the United States under Drs. Birthday Zhang, Lindsay Bassman, and Audrey Gomes. And I can't wait to share that with all of you guys. So first, a little bit about me. So I am actually a high school senior by US standards. So in 12th grade, doing a unique program called Middle College, where I basically take all of my classes at a local community college. And I've been taking a lot of higher level math, science, and information systems courses at the college level. And my ultimate goal is to pursue a PhD in quantum information security. I've just been really fascinated ever since I've been introduced to quantum through IBM's Qubit by Qubit course. Just like really interested in that. And I was also interested in information security. So just having a pathway where I can combine those two passions would be amazing. So as I mentioned, I was originally introduced to quantum through IBM's Qubit by Qubit course, which I believe all of you can still register for. And I've been reading about quantum and its applications in every industry ever since. And as I mentioned before, last summer, I was part of this amazing program under the Applied Computing for Scientific Discovery group, where I ran chemistry simulations on IBM's quantum hardware using a type of algorithm called a variational quantum eigensolver. And that is what I'll be talking about today. So I can get started. So a variational quantum eigensolver, or a VQE for short, is a quantum classical algorithm with many uses. We apply the VQE to find the ground state energies of molecules. And the reason why this is so important is because understanding the ground state energies of molecules can tell us how they will react with each other. And this can save us a lot of time and money in finding this information through lab experiments. So instead of going into a physical lab and experimenting with these to get these ground state energies, we can just simulate this on a quantum computer. And it's also essential to drug discovery and creating materials and much more. So a molecule is made up of atoms, like in the case of lithium hydride, lithium and hydrogen, as we see in the bottom diagram. And if we move these atoms closer together and farther apart and calculated the potential energy at each of these interatomic distances, that means in between the atoms, as you can see on the potential energy curve graph over here. To elaborate on that, a potential energy curve for a molecule is generated by changing the interatomic distance, let's say by 0.2 angstroms at a time, and calculating the new potential energy of the system at each point. So during my internship, we worked with a variety of molecules which had very different atomic configurations. And so we used an online 3D graphing calculator to visualize how we were changing the interatomic distances to ensure that we were modeling what we thought we were modeling. And here's a clip of what that would look like for a carbon dioxide molecule. The gray spheres are oxygen atoms, and the blue sphere is a carbon atom. And as you can see here, the interatomic distance is incrementing by 0.2 angstroms. So what we're looking for is the distance at which the energy is the lowest, aka the ground state energy. So the way the VQE works is that the quantum computer takes in an onsens, which is like an educated guess, and it's in the form of a wave function that represents the molecule. Then a classical optimizer alters that onsens, aka the guess, in an attempt to lower the energy value. So you have this educated guess at a point generated by the quantum computer, and then a classical optimizer is going to play around with that value to generate the lowest possible energy at that point. And this continues until the VQE has found the minimum energy of every point within the defined range, which is 0.5 to 4.0 angstroms in this case. So let's take a look at the results for that carbon dioxide molecule. The VQE energies are a product of the quantum classical algorithm, and the exact energies are what the energies are supposed to be at each point based on purely classical computation. And this graph is a visual representation of this data. And this second graph over here is just a zoomed in version of the error between the VQE and the exact energies on the tail end. And you can see that the two lines are still very close together, with differences in the hundredths place, which is what we want. That tells us that our VQE algorithm is doing well. And so the reason we're comparing the VQE and to the exact is to evaluate how good our quantum computers are at their part in the VQE process. In the future, when we try to model larger molecules, we hope we're confident enough in our quantum calculations so that we no longer need to compare them to the classical equivalent. So our graphs would just have one line, the VQE energy. Keep in mind that we can only calculate exact energy on small molecules because running through all of the possible configurations at each interatomic distance to find that lowest point takes a significant amount of time and classical computing power. That's why we're using quantum computing in chemistry, because a quantum computer can run through all of these configurations at once, compared to a classical computer that can only run through a few at a time. And as I spoke earlier, the VQE goes through this iterative process to find the lowest energy value at each interatomic distance. The wave function representing the molecule, aka the onsens, is fed into the quantum computer, which calculates its energy. And after the energy is calculated, it's given back to the classical optimizer, which varies the onsens to try to reach a lower energy. Think of this as being in a valley and wanting to reach the lowest point. Based on your previous steps, you try to determine the direction in which to take your next step to reach the bottom of the valley. And this is what that classical optimizer does. It updates the onsens based on the changes that seem to reduce the energy. And to improve our VQE, we tried out a few different optimizers, such as the stochastic gradient descent, constraint optimization by linear approximation, or COBILA, and the sequential least squares programming optimizer, or SLSQP. Of the optimizers we tried, COBILA consistently converged to a good optima, and it was quite stable. COBILA is a gradient-free optimizer, which iteratively approximates the function with linear programs. And SLSQP, the second best optimizer, also attempts to optimize the function, but it uses the gradient. And while it performs well on shorter interatomic distances, it becomes quite unstable as the distance increases, as we see in these graphs. They're both constrained optimizers, meaning they limit the changes to a feasible region, lessening the likelihood of unreasonable values like all the way up here or all the way down here. Traditional gradient-based optimizers like Atom tend to have worse performance, and it seems that the gradient-based optimizers are sometimes stuck in local optimas. In contrast, COBILA is a gradient-free optimizer that has a little bit more ability to search over the problem and find better optima. So we also experimented with the number of iterations or steps the optimizer takes. With more iterations, the steps the optimizer takes to reach the bottom are smaller and more refined, meaning that it is less likely to end up in local minimums. Think of a local minima as the optimizer getting stuck in a divot of the hill, thinking it has reached the bottom of the valley, and the points where the optimizer got stuck in local minimums can be seen in the spikes of the graph where the optimizer failed to reach the minimum value, like here, here. So all of the potential energy calculations that in graphs you've seen so far were generated on what is called a state vector simulator, which is where we can simulate what the results of an experiment would look like in a perfect world, where qubits and quantum computers produce no errors. Unfortunately, we have not yet reached that reality, and there are a lot of errors that result from noise, which can be from interference in the environment, unwanted interactions between qubits, or just any case where there is energy that's unaccounted for. And one way of observing the effects of noise would be running the experiment on a real quantum device. But unfortunately, that means waiting in a long queue to use a publicly available computer. So we resorted to just importing noise models from some of IBM's hardware onto a chasm simulator, where we can simulate the results of an experiment in an imperfect setting, which is what you see here. So it's kind of like we're running on the real device without waiting in line. In the bottom left, we have the carbon dioxide calculations from that state vector simulator, that perfect world. And on the right side, we have results from running the same calculations on the chasm simulator, that imperfect world, with the noise models from 1, 5, and 7 qubit quantum computers. And these use noise models from 3 of IBM's real hardware devices. This one has since been retired, but these 2 are still active. So we can see that these 3 curves are not very smooth. They have quite a few bumps, and that's just for a very small molecule. Now imagine trying to run an experiment for something much bigger, like a protein molecule. You can start to understand why noise is such a big issue in quantum computing, especially when we reach that point when we can no longer compare our results through classical equivalent, aka the exact energies. Because remember, the classical computations require just a lot of time and resources. So it's very hard to calculate those exact energies, which is why we're trying to move away from them and towards quantum computing. It's more efficient. So if we're forced to rely on our quantum computers alone in the future, but they're very noisy, we can't really do anything with our results because they won't be completely accurate. So what can we do to mitigate the noise? Let's explain in a little more detail. So we explored noise and mitigation techniques using a quantum circuit to determine the magnetization of a material over time. So we did a lot of work with simulating how atoms in molecules were reacting in terms of their energies. And now we switched gears a little bit to look at the magnetization of a material. A material's magnetization depends on how aligned the spins of its atoms are. We created our model based on a spin chain of the material MOSE2. MOSE2 has magnetized by the replacement of some molybdenum atoms by rhenium atoms, which have 1 extra electron compared to molybdenum. And because of this, the spins of the atoms in the material align to generate magnetization. We wanted to explore the effect of altering the number of qubits and changing the excitation factor on the magnetization of our material. So we created a Hamiltonian, or a representation of the total energy of the system using an Ising model, which determines magnetization by taking the nearest neighbors of each atom and determining how aligned their spins are. So I'll pick an atom in the spin chain and look left and be like, hey, what's your spin? And I'll look right and be like, hey, what's your spin? And then use that to determine magnetization. And we can see in the diagram, if the spins of the neighboring atoms are facing the same direction, the material is magnetized. But if the spins begin to lose alignment, they lose magnetization. And if they're facing in opposite directions completely, the material is not magnetized at all. And this is why we see the effects of excitation change between different numbers of atoms in our spin chain. In a 4-atom spin chain, the 2 center atoms will have 2 nearest neighbors on both sides. So there are more atoms to compare spins to. Whereas in a 2-atom spin chain, each atom only has 1 nearest neighbor. And finally, we want to explore how we can implement different techniques to mitigate the noise in our system. And one of the major manifestations of noise is a measurement readout error, where noise causes an output to be perturbed before it can be returned to the user. To combat noise, readout error mitigation can be applied. The ideal output of the circuit, which is calculated using a classical computer, is compared to the noisy output, which is calculated using a quantum computer. If you're familiar with linear algebra, a matrix is then crafted that will return the noisy output when multiplied by the ideal output. And the inverse of that matrix is taken to create a matrix that, when multiplied by the noisy output, will result in the ideal output. So essentially, we're trying to reverse the noise with these matrices. And the graphs in order from left to right are the state vector simulator, the ideal world I mentioned earlier, then the chasm simulator, which runs the circuit in an imperfect setting, and we can see that the graph becomes shakier. To the right of that, we see the further effects of adding noise by adding a noise model to our chasm simulator. And then finally, we can see how the graph becomes much smoother, similar to how it looked in the state vector simulator graph, when the readout error mitigation matrix is applied, aka when we try to reverse that noise. So as we've seen, there are some really cool things we can do with quantum, from graphing potential energy curves of molecules to observing the magnetization of a material over time. But we've also seen the unpleasant effects of noise to those experiments, and finding ways to mitigate or work around that is a critical part of quantum research right now. And I would like to give an enormous thank you to my mentors for taking me on this incredible journey of researching, learning, understanding, and debugging. And here are the tools we used over the course of this internship to make our work possible. So thank you.
Awesome. Thank you so much for the talk, Sabina. It was really, really amazing.
Okay, so now I will, I know that was a lot of information. So please don't hesitate to put questions in the Q&A box.
I can see already some questions that I can ask you here.
Sure.
Okay, so here's, there is, how did you do the simulations?
So it requires, so we have, IBM has this quantum like experience or quantum lab. And there are different types of labs, like Google Colab also has one where you run the Qiskit programming language. And so you program the simulations using the Qiskit programming language. And you can actually see, I think the Qiskit textbook actually has a sample of this quantum chemistry with VQE. Quantum chemistry isn't the only thing that you can do with VQE. There's a lot of applications with finance and other things. So you can definitely explore how to do those simulations yourself in the Qiskit textbook, I believe.
Awesome. I will afterwards share the link. But all the comments says here that it was amazing presentation. So, well, next to the other question is, what is the exact energy? How do you obtain it?
So an exact energy is calculated by a classical supercomputer. Basically, there are, I don't know too much because it's like it's done by a supercomputer, but it's basically like trying to do what a quantum computer does at a smaller, like, because these are simulations, right? Like, so they basically have these massive databases of all of these like energies that you calculate, like in a simulated environment. It's kind of hard to explain, but like they have these like big databases where they store all this information, and that's where they pull these exact energies from. But it's very hard to calculate those exact energies. They take up a lot of resources. So that's why we're moving towards quantum computing. So we don't have to refer to these massive databases.
Great, thank you. Well, here I have another one, and it says, why does noise affect quantum computers?
Noise affects quantum computers because I think I mentioned qubits, the quantum bits, they're very unstable. Jaya Kumar was talking about decoherence. It happens very quickly. Like qubits are very unstable, and that's why we have to keep them at like sub-zero temperatures, like very close to absolute zero, to limit that decoherence as much as possible. And so like any interactions, if you have any like extra particles, anything in the environment where a quantum computer is running, that disturbs the qubits and makes decoherence like much faster. So that's why noise affects quantum computers, is because they're like so much in the environment, like all these other particles and light particles and all this stuff that creates noise in the environment.
Great. So yeah, and that's one of the key points that now scientists and people are working in now in the field of quantum computing, like trying to stuff like this problem. Well, I have another question here that is, what is quantum simulator?
Oh, the QASM simulator. So the QASM simulator is like, I believe it was developed by IBM. It's like their version of like, because accessing like a real quantum computer is like IBM has some publicly available, but they're very small and you have to wait in line. Like if you want, like you need a query and it's like waiting in line with a ticket to run your simulation. So instead of having to wait in line to run a simulation, you can just do it on demand with this Chasm simulator that kind of like simulates what a quantum computer would do. And you can like, when you're programming this, you can kind of like choose like, oh, I want the noise model from IBM. Sorry, hold on, where is it? Like, let's say I want to simulate the quantum computer, IBM Q Bellum, and it's a 5-qubit quantum computer. And so I can run it on a Chasm simulator and then tell using Qiskit saying, hey, I want to simulate it as if I'm running it on the actual IBM Q Bellum.
Awesome. So, well, next to the other question is, Dilek is asking, how do you obtain the noise and do you use it as a baseline?
A baseline. How do you obtain the noise? So there is like, well, all of the noise models, they're kind of like estimates on what would happen. Like if I were to run an operation on IBM Q Bellum, like how much noise? And that's done using a lot of calculations and a lot of testing by whoever runs these quantum computers. They kind of run up like thousands of operations and see like, okay, how much error would there be? And they kind of calculate that error and like put it in this big matrix that then you can apply onto your results to like simulate. So like, yeah, I hope that answers like your question about noise. And then using it as a baseline, yeah, it is kind of a baseline because that's like our starting point. Like we see like this orange graph, that's the VQE energy, that there's like quite a bit of error, especially over here. And that's like our baseline, like this is how much we need to improve our algorithm, our VQE, to get to this nice smooth line. So it's a baseline of how much error do we have and how much work do we still have to do to get to this perfect line.
Thank you. Well, and here I have another question from Carolina, and it's, do you have any textbook or videos that you recommend for beginners?
I definitely recommend the Qiskit textbook. I will double check right after this if Qiskit still has a section on quantum chemistry with VQE, but if you just search up like quantum chemistry with VQE, you'll find that there's a library, a Qiskit library, a programming library called Qiskit Nature, and they have a lot of some documentation on how to run these with that programming library. So I recommend, as Jai Kumar also mentioned, like just finding tutorials, and they'll have like answers and step-by-step guides on how to run a simulation, and you can follow through that, use that code. It's, it's publicly available, and you can try that for yourself. And you can also, like, this shows a carbon dioxide molecule, but we ran like so many other ones, like water, methane, lithium hydride, beryllium hydride, like a lot of molecules, and you can experiment with that yourself. And you can put in those values, and you like, if you have any questions, you can of course reach out to me, but you can also reach out to, there are a lot of forums that talk about this as well. So if you have any questions about any like chemistry related things as well, there are a lot of chemistry resources out there.
And yeah, it's a line here, says his book also, that we're going to hear like in a couple of minutes. So you're so excited as well. But I wanted to also say that I post here in the chat like some links about Qiskit, the textbook, again in the Quantum Computing IBM website. And also if you want to learn about quantum computing a little bit, like some basics, you can also check it out, or Instagram page where we post like many contents. But yeah, I also wanted to ask you, Sabina, what are your like the main takeaways after this amazing internship that you did?
I think the biggest takeaway, because it was just a few months after I finished that Qubit by Qubit course, the Introduction to Quantum Computing. And I was like so excited and inspired to just like learn more and learn as much as possible. So I was reading different kinds of quantum textbooks, and it is challenging because they have a lot of linear algebra and very advanced concepts in there. I think like I came into the internship thinking like, okay, I have some idea of what's going on, you know. But then you realize that even like the PhD like researchers that I was working with, that they don't even know all of the answers. And you realize like quantum is like a field where like no one knows the answers. And that's very different from other fields, because in other fields, there are experts that like know the answer. And in quantum, it's still so new that like you're exploring alongside them, that there's no one, like if someone claims that they're an expert in quantum, I don't know, I probably would take their whatever they're talking about with a little grain of salt, because I don't think anyone really understands fully what's going on. So that was
Awesome.
my biggest takeaway.
So yeah, so in like in general, like keep learning about it, and well, I think that there was also challenging topics that you review, but well, you learned a lot and you did such a great presentation. So
Thank you.
thank you to you.
Okay, so thank you everyone for your questions for my presentation.